Some of you don't. It's okay, but we'll get there. But what this means then, right, if we now know the column correspondence property, we can think about this. What does this mean? This means that the sixth column is apparently 1/4 of the third column. If I did that right. Oh, this is the third column, right? I've lost track of what I was talking about. The third, okay, we got third column versus sixth column. The sixth column is 1/4 of the third column. This versus that. 1/4 of this is that. Yep. Let's see, what else can I tell you? The fifth column is like 1/2 of the second minus 1/2 of the third. Half of the second minus half of the third, so that's that, yeah. Study it, the patterns are all there, right? They may or may not be interesting to this problem, but they're there to see. Of course, this problem, the solution set is what? It's actually how many dimensional? How many parameters are there in the solution set? Well, we've got 1, 2, 3 pivot columns, which means we've got x4 and x5 as parameters. So if we write down the solution set for this problem, it's going to have 2 parameters in it, right? The standard form of the solution. Let's see if I write that down next. I probably do. So there they are, right? x1 is minus 4, x2 is x4 minus 1/2 x5, and x3 is 1/4. You see where the quarter came from? The quarter is this quarter, right? The reason this is minus x4 is because it's a plus 1 here, right? So when I rewrite this first row, it's x1 plus x4 equal to 0, which gives me x1 equals minus x4. x2 minus x4 minus plus 1/2 x5 equal to 0. When I move the x4 and the x5 to the other side, it changed from a minus 1 to a 1, and from a plus 1/2 to a minus 1/2, all right? All right. However, we can also look at this as a vector solution, all right? We can look at it as a vector solution. You see, the solution, V, this is an arbitrary solution, looks like this. And you can build it in 2 pieces. The x4 piece, the x5 piece, and also the piece that has nothing to do with x4 and x5. So what this says is that the solution to the system has the form of a linear combination of these 2 vectors and this kind of oddball over here. All right. So this is kind of neat. If we wanted to solve 2 systems, right, and they have the same coefficient matrix, all right? So like, notice the same equations, both of these, right? But the inhomogeneous terms are different. 1, 0, 1, 1, 1, 1. So if you think about the row reduction for both of these problems, it's the same as governed by the first 3 columns, because row reduction goes column by column, right? So what they're going to do to the 4th column in the augmented coefficient matrix would be different for these different problems, but this same set of row reductions is going to work. And so, like, what happens is you can just say, okay, here's the so-called or extended augmented coefficient matrix. So I take coefficient matrix, and instead of just augmenting by 1 inhomogeneous term, I do by 2. And I can just do one foul swooping row reduction on the whole thing and solve both of them at once. And in so doing, I find the solution to the first system is x is minus 1/4, y is 1/2, z is 3/4. And the solution to the second one is x equal to 0, y equals to 0, z equals to 1, right? Which is totally unsurprising if you look at this problem, because 1, 1, 1 is the inhomogeneous vector. So of course, one copy of the third column here gets it for you. Z equals to 1 is linear combination, just that, 0 these, 0 these, if we put x equal to 0, y equal to 0. So we can solve more than one system at a time like that. So now I explain the elementary matrices. Here's some further examples of those. Typical homework problem is like, I give you a row reduction and I say, okay, find me the elementary matrix which makes that row reduction happen, right? So I think you could figure that out, right? If I've showed you how to find the elementary matrices for like the row swap or the row addition or the row multiple, you could find similar elementary matrices for different row operations. It wouldn't be a big deal. This is just for giggles, but if you take the elementary matrix and you multiply on the other side, it does the same thing but with columns. So multiplication on the right gives you column operations, which I don't really do anything with. So yeah, there that is. So I've talked to you guys already about the linear combination problem. And here is a little bit more interpretation. Like, so here I'm asking the question, is 415 in the span of 2, -1, 3, and 1, 1, 1? That gives us this 3 equations and 2 unknowns. Notice here I'm using x and y rather than c1 and c2, which might make it feel less weird to you. All right, but x and y here are playing the conceptual role that c1 and c2 did at the start of this lecture. And of course, then you can do row reduction and you get this, and voila, apparently, yes, the answer is, it is in the span. It's 1 copy of the first vector plus 2 copies of the second vector. And you can see that. If I take this plus twice that, 2 plus 2 is 4, -1 plus 2 is 1, 3 plus 2 is 5, yay. And geometrically, what's going on here is that if we start from the origin and we look at all possible linear combinations of 2 vectors, that fills out a plane in 3 dimensions. So to ask if a third vector is also in the span of those 2 vectors is to ask if that vector also falls in that same plane. That's the meaning of the spanning question. You're asking if the third vector for a given 2 is in fact coplanar. And here's an exciting picture of it. So you have, I don't know if I can remember. Here's the vector from here to here, 2, -1, 3. I don't know where 1, 1, 1 is in this picture, but this is 4, 1, 5, which is where we're trying to get to. I think if I do twice 1, 1, 1, yeah, this going from here to here, if you think about tip-to-tail vector addition for a second, so if I add this from here to here, that's twice the 1, 1, 1 vector to get from here to here. So I don't know how much, I mean, it's a wonderful picture, right? Does it help you understand linear algebra? I'm not so convinced, but there it is. I defined span for you guys today, right? Set of all linear combinations. Let me try to skip ahead a bit here. This is another solid standard problem. I have 3 vectors, b1, b2, b3, and I want to know if 1, 1, 4, 4 is in the span of b1, b2, b3. All right? So what did I do? I'm asking the question, can we solve x1, b1 plus x2, b2 plus x3, b3 equal to w? But that is logically equivalent to finding the augmented coefficient matrix of this matrix. If I can do that, that means that w is a linear combination of these 3. Is it? I don't know. Do row reduction, get to this. Yeah, w is a linear combination of those 3. Apparently it's 1 times the first column minus the second column plus the third column. So the answer is w is b1 minus b2 plus b3. Column, I mean you got options, right? You can go into here and say, okay, so x1 equals to 1, x2 equals to -1, x3 equals to 1. So of course we get this equation, right? But the other way of thinking about it is the column correspondence property, which is I can see directly from this that it's first column minus the second column plus the third column to get me the fourth column, which answers the question as such. So here's one that didn't work out, because if we calculate the, if we try to answer the spanning question, it amounts to doing this row reduction, and we get an inconsistent system, which says that no, 0, 1, 0 is not in the span of 1, 1, 0 and 0, 1, 1. All right. So here's like the general setup. If I've got k vectors in Rn and I've got another vector b, I can solve this equation by Gaussian elimination of the corresponding matrix, where I just shove all the v1 through vk in the first columns of the matrix, and I put the desired vector to reach in the span in the last column. Then b is in the span of those guys if and only if that represents a augmented matrix of a consistent system of equations. All right. And yeah. Now, so that brings us to linear independence, which I'm not going to define linear independence today. We'll talk about that maybe next time. I don't want to hurry on that, but I did want to. Oh man. Well, so the next chapter is on invertible matrices properly. Anyway, so before I go on, is there any question about anything in particular? Like, so as you guys are working through the practice homework, if something doesn't make sense, you can like ask about that in here, you know? Like that is allowed. Even though I have solutions posted, like that doesn't mean you can't ask questions about it. So I'll start a class, you might be like, hey, I've got a question about this practice problem. You did such and so forth here, what's that about? You know, and maybe the answer is, oh, we're covering that next class. Maybe the answer is, I can tell you what the answer is, you know? So that's just like a general point of order going forward. But I guess this is as good a place to stop as any. I hope you start to appreciate the power of the column correspondence property. I cannot overemphasize its use. So, I personally did not learn it as an undergraduate, and it made my graduate linear algebra like way harder.